Okay, welcome to CALOP Eat and Learn seminar. I think this is the last Eat and Learn seminar in this academic year, 2025. So welcome. And today's speaker is Professor Eunjin in the computer science department. She will share her research work. Yeah, please welcome her.
Hello everyone. Today I'm going to talk about the massively parallel algorithms for geometric proximity problems. And this is joint work with Eunjin sitting over there. More precisely, in this talk, I'm going to talk about constant round MPC algorithm for the following fundamental geometric problems in doubling metric space. And these include the diameter problem, the closest pair problem, and the spanner construction, all nearest neighbors problem, and all k nearest neighbors problem. I will define those problems later, but the important thing is that the core of our approach is to construct the well-separated pair decomposition. In this talk, I will first define our setting, including the MPC model and the doubling metric space and the well-separated pair decomposition. The first thing is the doubling metric space. The doubling dimension of a metric space is defined as follows. It is the smallest integer d such that any ball of radius r can be covered by 2 to the d balls of radius r/2. For instance, the Euclidean space has a constant doubling dimension if d is constant. To see this, observe this ball, the red ball. It can be covered by 7 balls with half radius. So the doubling dimension of a two-dimensional Euclidean space is at most 7. And in this paper, we are dealing with doubling metric space, and we will design a constant round MPC algorithm in doubling metric space. So this leads to an algorithm in a constant dimensional Euclidean space as well. In the case of Euclidean space, a point is associated with its coordinates. So given 2 points with their coordinates, we can compute their distance in constant time. But in this general doubling metric space, a point is not necessarily associated with its coordinates. So in this case, we use the following model. We assume that the distance between 2 points in doubling metric space can be computed in constant time instead of using their coordinates. Our paper focuses on algorithms in doubling metric space, but in this talk, I will focus on Euclidean space. So, and I will briefly talk about doubling metric spaces at the end of this talk. Okay, then let's talk about the MPC algorithm. Massively parallel computation model abstracts modern large-scale parallel computing frameworks such as MapReduce and other things. In this model, we have a number of machines, and using those machines, we want to solve a specific computational problem. And each machine has its local memory, and we use S to denote the size of the local memory. And if we have M machines, then the typical setting is that the total space is linear in the input size. If our input consists of n points, then we assume that the total memory space is linear in n, near linear in n. So M and S are sublinear in the number of points. And because the total memory space is linear in n, we can store all the points across the machines. So initially, we assume that the input is distributed across the machines. And the algorithms in this model consist of synchronous rounds. In each round, each machine performs local computation. And at the end of each round, they communicate with each other. More precisely, each machine sends messages to other machines. And here a critical constraint is that the total size of all messages received or sent by a machine is order of S. So at the end of each round, this machine can send messages to some other machines, but here the total size sent by this machine is order of S. Here S is the size of the local memory space. It is possible that this machine sends the same message to different machines, but in this case, when we talk about the total size, the messages are considered distinct messages. So we do overcounting. Okay. This is the general setting in this model. And I will give a simple example, broadcasting. In this problem, a machine has some message of size S, and the goal is to send this message to all other machines. And the general assumption in this model is that the local memory space is n to the some constant. Okay, here, a straightforward approach is as follows. In the first round, at the end of the first round, so let's first assume that this machine has a message of size S, and we want to send this message to all the machines. A straightforward approach is as follows. At the end of the first round, it sends this message to the second machine. Because the size of the message is order of S, it can be done in constant rounds. So at the end of the first round, those two machines have the same message. Okay, then in the second round, this machine sends its message to the third machine, and this machine sends its message to the fourth machine. Then at the end of the third round, those four machines have the same message. Then in the next round, those four machines send their messages to the next four machines, and so on. In this way, after log n rounds, all the machines have the same messages. But here, we have a better or efficient algorithm. Okay, when we talk about MPC algorithms, we measure its performance as the number of rounds. So we don't care about the computation time. We only care about the number of rounds. This is a constant rounds algorithm for broadcasting. First, we use a tree with branching factor of S. So here, the branching factor, the number of children here is S. Again, S is the space of the local memory. Then, because the number of machines is n over S, the height of this tree is constant. Here, S is n to delta, and the branching factor is n to the delta, and the number of machines is almost n. Therefore, the height of this tree is constant. Okay, then the algorithm works as follows. In the first round, And in this tree, each node corresponds to a machine. So this root corresponds to the first machine, and its children corresponding to the next S machines, and so on. Okay, this algorithm works as follows. In the first round, M1 has a message of size S. That is, this message consists of S words. So at the end of the first round, M1 sends ith message to the ith child. So the first child now has the first word, second child has the second word, and so on. Recall that it consists of S words. So the total memory sent by M1 is order of S. So it can be done in a single round. And for each child, it receives just a single word. So it can be done in constant rounds as well. Okay, in the second round, each child sends its message to all those siblings. Because we have each child has at most S siblings, and it sends a single word to those S siblings, it can be done in constant time as well, constant rounds as well. Then in this way, at the end of the second round, all those S plus 1 machines have the same message. This child now have all those words. And this requires just a constant rounds. And then we can recurse on each subtree. Because the height of this tree is constant, the total number of rounds required by this algorithm is constant as well. So do you have any questions so far?
So everyone sends S-ith words to the...
S-ith word?
Everyone sends the ith word to the ith.
Yes.
Just one word? Or?
Just one word, ith word. So this message consists of S words. The number of words here is S. So it sends the fourth words to the fourth child.
In the next step, the fourth child sends the word to another.
All other siblings.
He got one word. And
Yes, so let's look at this. Here, at the end of the first round, this machine has a single word, the first word. And in the second round, it sends this single word to all its siblings. Okay. Then at the end of the second round, each child has all the S words.
So that means you have M machines, then M divided by S times 2 times we need.
S is the local space.
Because the S machines, they got all messages in 2 rounds.
Yes.
So if you have M machines, then M divided by S
Ah,
times 2.
Okay, after doing this, we repeat this procedure on those subtrees. So here, look at this subtree. It is.
Subtree has also another machines.
Yes. Each node corresponds to a machine. And look at this. The height is decrease by 1. And this root has the message. So we can recurse on this subtree. Then the number of recursion steps is constant.
So in my understanding, in 2 steps, S machines will be covered.
Yes, right.
Then the next round, S.
Yes, the first 3 layers can be covered.
One machine, S machine, S square.
Yes. Because the number of levels is constant, the total rounds required by this algorithm is constant.
Can you explain why the height is?
Okay, the height is log S to the n. This is a branching factor, and this is the number of machines. And S is n to the delta by our assumption. This is a standard assumption in this field. And delta is a constant. So okay, so in this model, we can send message to all machines in constant number of rounds. And the second example is sorting. We can sort n elements in constant number of rounds. We can do this as follows. Initially, we have n elements, and they are sorted across m machines. Then, in the first round, we sample square root of s items uniformly at random. And we will use those items as pivots. Because the number of pivots is small, we can send those pivots to the first machine. Then we use the broadcasting algorithm to send these pivots to all the machines. Then now every machine has those pivots. Then based on those pivots, they compute the number of items between 2 consecutive sampled points. So for instance, let's imagine that the items are sorted in the increasing order. This is the desired output, but let's imagine that we have the sorted list. And they are pivots sampled from the input elements uniformly at random. Then those pivots subdivide the sorted list into root S sublists. And our goal is as follows. We want to rearrange the elements so that the first part of the machines consists of elements in L1. And the second part of the machines contains the elements in L2. So the elements in L1 are not necessarily sorted yet. But we want to ensure that at the end of the constant rounds, L1 are stored before the other elements. So we can do this as follows. We first send those pivots to the all machines. Then each machine has a small number of points. And in addition to those points, we have pivots. Then based on those pivots, this machine can subdivide its elements into those sublists. Okay, let's focus on a single machine. It has S points given at the beginning of the first round, given as an input. And we have root as pivot. Okay, this is the S point given to the first machine. And we have pivot. So we can determine each element. We can determine for each element whether it is contained in Li. We can determine the index of the sublist where this point is contained.
When pivots are determined, should we sort those numbers first?
Yes, during each round, we can do local computation.
So when M receive the square root S items,
Yes.
then it should sort them, then send to the information to
Yes. We can do this. Then in each machine, we have S sorted items and root S sorted pivots. Okay. Then using those pivots, each machine can determine the index of sublists where each item belongs.
So it's kind of a logic sort idea.
Yes, right.
We don't have to process one by one, but
Yes, right. It is a kind of merge sort or quick sort, but the difference is that in the quick sort algorithm we use a single pivot, but here we use root S pivots. Right. If we use a single pivot, then the number of recursion depth is log n. But because we have root S pivots, the number of rounds is constant. Okay, do you have any question for this thing? Okay, so in this way, after a constant number of rounds, we can compute the elements contained in L1 and the elements contained in L2 and so on. Then we sort, we rearrange the elements in a proper way. Then we recurse on those parts. We recurse on each sublist. And because of randomness, we can ensure that with high probability, the size of each sublist is n divided by root S. So with high probability, we can ensure that the number of rounds is constant.
Have you experimented with the actual computation time?
Computation time? I think the total computation time would be log n. But in this model, our focus is to optimize the number of rounds, not the computation time. But
finally, try to find out quickly the constant time, the meaning of constant time.
constant rounds.
Constant round.
Yes.
Constant round. So the final goal should be the fastest. Am I wrong?
Okay, our goal is to sort the n elements in constant number of rounds.
Yes.
So at the end of the rounds, our desired output is the sorted list.
Yes.
Okay, so suppose all the numbers are quite randomly sequenced in the very beginning. You can just, for the random choose, you can choose the first square root items. It will be okay.
Oh, yes, yes,
Suppose there are some kind of tendency.
yes.
So randomly choosing that kind of procedure may take time more than square root S times.
Yes, it can be done by slightly modifying this broadcasting algorithm. For instance, here we choose root S elements uniformly at random. Here we choose root S items uniformly at random. Then we merge and reduce those pivots by traversing the tree from bottom to the root. But I mean, sampling can be done in constant number of rounds. And it takes linear time in the worst case.
Is chosen to make to reduce the ROM. Can is it better?
It is an arbitrary value. You can increase it to S.
Up to S.
Yes. But because we want to, we need the broadcasting algorithm, it should be at most S. But any value of S to some constant is fine in this case.
So in the kind of shortest path algorithm, there's a kind of bucket type of algorithm.
Yes?
There's somehow similarity between this because we are going to partition the items. Not exact sorting, we are going to partition to separate places, and then later on we are going to sort them. Not sort, we are going to compute. We are going to compute later.
Yes?
Bucket type of algorithm. But here we each after partition into separate parts, then they will handle themselves. So it's quite interesting idea for this massive parallel computing.
But in the MPC model, a famous conjecture is that the shortest path cannot be solved in constant number of rounds. Yes, we might be able to use those ideas, but the running time, the number of rounds, might be larger than constant.
As an engineer, I don't know if there is an experiment. So like we sort 10 billion numbers, and we have a parallel machine, 100 parallel machines. How fast is it compared to just a single machine? As a scientist, I was just, as an engineer.
Well, it depends on how. It depends on the number of machines you have and the space of each machine you can use. But theoretically, the number of rounds is constant, and if in each round the running time is nearly linear in the local memory space. So the parallel time would be n to the delta.
So far, you assume that all machines have the same computing power.
Yes, yes.
Suppose in real that they may have heterogeneous. Let's say fast machine and slow machine. Can we generalize this result to the kind of fixed number of?
Yes, as far as I know, there exists a variant of the MPC model which can address that issue, but I'm not aware of any specific algorithm in this model.
So the sample size and the number of people should be the same.
The sample points are pivot.
Okay. So sample point, the number of sample points.
We use those sample points as pivot.
Should be same, but even though we choose the rootedness sample, we can pick more people, like number of machines.
Sorry, I don't understand your question. So, okay, what I said is that among n items, we sample root S items uniformly at random, and we use those sample points as pivots. So we broadcast those pivots to all the machines, and then. 죄송해요, 질문이 뭐였죠?
그러니까 꼭 샘플로 피벗을 해야 되는지. 샘플은 여러 개 볼 수 있지만, 샘플을 테스트 볼 수 있지만, 걔는 어떤 전체 데이터에 좀 디스트리뷰션을 파악하기 위한 걸 하고, 피벗은 더 많이 해야 돼요. 머신 개수만큼 하는 게 자연스러운 것 같아요.
Number of people cannot be more than number of sample values.
그러니까 샘플을 한다면 그걸 피벗으로 쓰는 건데 그 피벗을 더 많이 쓰면 그 피벗을 어디서 맞아요. 피벗을 고르기 위해서 샘플링을 하는 거예요. 네. 더 큰 피벗이 필요하면 더 큰 샘플을 하면 됩니다. 그렇죠.
이제 만약에 S보다 만약 가까이 오신 로트 S에 피벗을 나왔다고 해서 얘가 로트 S께 이제 메모리를 안 차지 않을까? 내가 피벗을 골라야지 하면 다른 머신들은 그 피벗을 모르는
그 말이구나.
그 임의로 잘 큰 머신이 피벗을 모르는 거는 이제 알고리즘 자체적으로 문제가 있을 수 있어요.
로컬하게 피벗을 고른다는 뜻이셨나요? 네.
저도 제가 잘 이해해요.
네.
샘플 중에 있는데 피벗을 좀 이븐리 디스트리뷰트를 하면 그 사이트 들어가는 것도 좀 비슷해진다는 그런 의견.
뭐 약간 저는 머신마다 좀 이분하게 나누는 게 좋을 거라고 생각해요.
그 피벗이 모두가 다 공유를 해야지 그걸 머지할 수 있어요. 각 머신이 다 똑같은 피벗을 가지고 있어야지 나중에 머지를 할 수 있는데, 그래서 머신마다 이제 각자의 피벗을 그러면 이렇게 머지가 힘들어서 피벗은 모든 머신이 다 공유를 해야 됩니다. 그래서 이제 제너럴 샘플링 쓰는 거고, 브로드캐스팅 써야 되니까 샘플 사이즈가 최대 S까지밖에 안 되는 거죠. 그래서 아까 말씀하신 대로 그 퀵소트 알고리즘이랑 똑같은데 피벗의 개수만 조금 늘어난 거예요. 그것 때문에 퀵소트 자체가 이제 이게 자연스럽게 패러럴라이즈 될 수 있잖아요. 근데 우리는 머신의 개수가 좀 더 머신의 개수를 많이 쓸 수 있으니까 그 머신 개수의 그 장점을 활용하기 위해서 샘플을 더 많이 하는 거죠. 그랬더니 전체 라운드 수가 로그 루트 S n이 되어서 전체 라운드 수가 상수가 됩니다. 계속해도 될까요? Okay, then, and one thing I should mention is that there is a classical parallel model called PRAM model. MPC model is relatively new, but there already exists a classical PRAM model with a different definition and different setting. And there is a close relationship between the PRAM model and the MPC model. More precisely, any PRAM algorithm that runs in log n parallel steps using polynomial number of processors can be simulated in log n rounds in the MPC model. So as a consequence, let's think about the sorting problem. It is known that there exists a PRAM algorithm running in log n parallel time. Due to this fact, this PRAM algorithm immediately leads to a log n rounds MPC algorithm. And in the case of the PRAM algorithms, there is a lower bound. It is known that any PRAM algorithm requires log n parallel time. But this lower bound doesn't extend to the MPC model. And in fact, we just saw that sorting problem can be solved in constant rounds in the MPC model. The previous algorithm is randomized, but you can make it deterministic. So this indeed shows that this lower bound doesn't hold for the MPC model. Because this result is very general, any problem that admits log n PRAM algorithm can be solved in log n rounds in the MPC model. So in this field, an interesting problem is to design constant rounds MPC algorithm for problems that admit log n parallel step PRAM algorithm.
Can you explain me about the PRAM algorithm and the meaning of parallel time compressed?
PRAM algorithm, we have a number of processors, but here instead of having local memory space, they have a shared memory space. So and the parallel step is just a parallel time.
Not a sum of time, but
the max of the computation time among all the machines. And in this paper, we show that in a doubling metric space, those problems can be solved in constant number of rounds in the MPC model. And previously, it is known that some problems here admit constant rounds MPC algorithm in the Euclidean space, but there is no unified algorithm for solving all those problems in constant number of rounds. Instead of that, in the Euclidean space, in the PRAM model, WSPD can be constructed in log n parallel time. So we can construct WSPD in log n rounds in the MPC model. But in the doubling metric space, nothing is known. So in this paper, we showed that in doubling metric space, we can construct a WSPD in constant rounds, and this gives constant rounds MPC algorithms for all those problems. Okay, then I will define the notion of WSPD. Okay, we are given a point set, then the number of pairs in this point set is quadratic. So the number of different pairwise distances is quadratic as well. But WSPD, well-separated pair decomposition, approximately represents all pairwise distances of points using a small number of well-separated pairs. I will define it later, but for this, I will define the notion of well-separated. We say two point sets A and B are well-separated if their maximum diameter is at most some constant times their distance. So this is the distance between A and B, the smallest distance between any points from A and B. And this is the diameter, the maximum distance of points in A and the maximum distance of points in B. And if this red line segment is much longer than those blue line segments, we say that A and B are well separated. Here, a good thing is that we can use this distance as an approximate distance between points in A and points in B. In particular, we can show that for any 2 points, A from the first point set and B from the second point set, their distance is larger than the red line segments and smaller than the distance between A and B times some constant. So the number of distances here is quadratic. However, we can use this single value to represent their distances. Okay, in the case of well-separated pairs, we can use a single value to cover all pairwise distances. And it is known that the well-separated pair decomposition is defined as follows. It is a set of well-separated pairs. So here, this is well-separated pair, and this is well-separated pair. And the constraint is that for any 2 points from the initial point set, there exists a unique pair such that A is contained in the first element and B is contained in the second element. For any point pair A and B, their distance is covered by one of the L pairs. In this case, we say that those pairs define a well-separated pair decomposition.
So AI don't have to be disjoint.
Yes, right.
But if you consider A and B, then the A set, B set should be identified.
Yes. A single point can be contained in several different pairs, but given a point pair, there exists a unique, well-separated pair. Okay, as I mentioned earlier, to represent the pairwise distances between A1 and B1, we can use a single value. And because of this property, we can ensure that L, the number of pairs here, L values are sufficient to represent all pairwise distances in P, or points in P. So if L is small enough, we can compactly represent all pairwise distances. And in many applications, for each pair, it is sufficient to keep only 1 point pair. Or it is sufficient to keep this red line segment. So the space complexity required to represent this WSPD is linear in the number of pairs, in this case L.
So given a point, is it easy to test the membership to
It depends on the representation, but if you keep only one point pair for each pair in the WSPD, you cannot do this. But in many applications, you don't need to identify the pair where this point pair is where this point belongs. And it is known that in the Euclidean space or in a doubling metric space, there exists a WSPD with only n well-separated pairs. L is n in the Euclidean case, or doubling metric space. And once we have this representation, you can solve all those problems in constant rounds very easily. As an example, let's take the closest pair problem. So we are given a point set in the Euclidean space or doubling metric space. Then the goal of this problem is to find 2 points whose distance is minimized. We can compute this closest pair very easily once we have a WSPD. Okay, let's assume that we have a WSPD with linear number of pairs, and AB is the closest pair. Then you can show that there exists a pair in the WSPD where A consists of a single point A and B consists of a single point B. You can prove this using the definition of the WSPD. Then once we have W, we can find the exact closest pair in constant number rounds by looking at the pairs in W in parallel. As I mentioned earlier, for each point pair, we keep just one representative point pair. In this case, A, B, this closed pair should be a representative pair. Therefore, by comparing the distances of all representative pairs, we can find the smallest closest pair. And for all other problems can be solved in a similar way.
So parallel, that means each machine can, each machine is in charge of
A number of pairs, yes. Yes. At the end of the parallel algorithm, W, those n point pairs are distributed across the machines. In other words, each machine has S different point pairs. So it computes the closest pair, and the second machine computes its closest pair, and then by doing this in a reverse way, bottom up, using the bottom up approach, we can merge the solutions. And finally, we can get the closest pair.
So here n is given.
N is the number of points.
Number of points. So we have a metric space. All points are given. We know that these points lie on the metric space.
Yes.
We don't enumerate all the points in the metric space.
We are given n points, and in our model, we assume that given 2 points, their distance can be computed in constant time. So under this model, we can compute the WSPD in constant rounds consisting of linear number of pairs.
So if we are given WSPD, then we can find A-B pair which contains only one element each, and they are the closest pair.
Yes, yes, yes. More precisely, we have n point pairs. Yes, this point pair represents one of the L well-separated pairs. Right? We have L well-separated pairs, and our algorithm picks one point pair as a representative of A, B. As an output of our construction algorithm, we are given n different representative point pairs. Then this result implies that by considering those n point pairs, you can find the closest pair. Because one of the representative pairs is the closest pair.
So this is kind of general question. MPC is motivated by parallel computing.
Yes.
In computer science.
Yes.
Is there any real world, I mean, from the nature, is there any similar behavior? Because it's the most possible utilization of each resource as much as we can, and we are going to minimize number of rounds. Right?
Yes.
So we try to make them busy.
Yes.
So in nature, for example, some bees or some insects, they try to achieve a certain goal in a short time. They have to separate their works and so on and so on. Is there any kind of some motivation of this idea, or is it just from the very computer parallel machine computing?
Sorry, I don't know any such an example,
Yeah,
but this model initially originated from the large-scale parallel computing frameworks.
So as I understand, we have very large data, so that local machine cannot compute it efficiently, so we need multiple machines. So now the bottleneck becomes the communication around the machine, not the local computing.
Right. If the data is very large, and our machine has a small-sized memory, then we want to design an algorithm that use many different machines. In this case, we can use this model.
Just another question. Why do we assume the synchronized communication? Is there any specific reason, or?
The main reason is that it makes algorithm analysis easier. If the round is not synchronized, I'm not sure if we can analyze algorithms in a clean way.
WSPD 자체는 어떤 식으로 만들어요?
WSPD 자체는 제가 아마 시간 없어 말씀 못 드릴 것 같은데, 일단 그 유클리디안 스페이스에서는 쿼드 트리 방식으로 만듭니다. 그러니까 원래 시퀀셜한 경우에는 이제 쿼드 트리라고 공간을 계속 4분할하는 거예요. 이렇게 하고 이제 이걸 계속 쪼개서 그 박스가 점 하나를 포함할 때까지. 근데 그렇게 하고 나면은 이제 WSP를 어떻게 만드냐면 각 셀마다 이제 이 셀마다 이웃들을 볼 거예요. 이렇게 해서 요거마다. 그래서 이웃들 중에서 이제 사이즈가 큰 거. 이렇게는 안 생겼겠죠. 잠시만요. 각 점마다 요것보다 한 칸 더 큰 걸 본 다음에 요것들의 이웃을 볼 거예요. 그럼 뭘 증명할 수 있냐면 이 상수계 이웃들 중에서 하나랑 이제 연결을 하면 된다. 그러면 그렇게 만들어진, 그러니까 이렇게 모든 페어를 다 보는 거죠. 그러니까 요거랑 요거, 요거랑 요거, 요거랑 요거 이렇게 다 보면은 다 이누머레이트 하면 그게 WSPD가 된다라는 걸 증명을 할 수 있습니다. 근데 이제 각 셀마다 상수계 이웃을 보게 되는데 셀의 개수가 리니어 개니까 페어의 개수가 리니어 개가 된다. 네. 리니어는 아니고 n log phi. 하이트가 이게 phi라고 하면 n log phi인데 이걸 조금 더 이제 필요 없는 셀 좀 지우고 그러면 리니어 개가 됩니다. 유클리디안 스페이스는 쿼드트리 만든 다음에 이제 각 셀별로 이웃에 있는 것들만 이제 보면 된다. 이거 증명하는 거는 뭐 그렇게까지 복잡하진 않은데 그 컴퓨테이션 지오메트리에 되게 되게 옛날 결과입니다. 그 텍스트북에 나오는 아주 중요하고 기본적인 결과예요.
그 n 포인트가 있으면 n 스퀘어 페어로 안 보고
네네네.
이런 식으로 빠르게 할 수 있는.
그러면 좋은 점이 원래 n제곱계의 디스턴스를 우리가 다 봐야 되는 상황에서 예를 들어 뭐 클로지스트 페어 같은 거 볼 때 n제곱계를 다 비교해서 그 중에 미니멈을 찾으면은 n제곱 시간이 걸리니까 그렇게 하지 않고 이런 식으로 쿼드 트리를 만들어서 요 디스턴스만 봐서 제일 짧은 페어를 리턴하면은 리니어 시간에 클로지스트 페어를 찾을 수 있다는 결과입니다. Okay, I think we don't have enough time, so I will skip the details of our main algorithm. So what I want to say is that we can construct a WSPD in the Euclidean space using quad tree in a constant number of rounds. And in fact, to obtain a WSPD in the MPC model, we simply parallelize the known construction for the WSPD in the Euclidean space. We just parallelize the known sequential algorithm in the Euclidean space. However, in the doubling metric space, we need to design a new construction algorithm to get the output in constant number of rounds. And finally, we can obtain a WSPD in constant rounds using this number of machines. And the local memory space is n to the delta. Delta is the parameter we can control, we can choose. And using this, we can solve all those problems in constant rounds. Okay, that's it. Thanks for listening to my talk.
Decide the number of the machines as well. Is it possible? Is it part of the algorithm design?
The number of machines can be determined by a user. It is a part of input.
Then we need to determine S or absolute what? So you said number of machine is given.
I mean, we can determine the local memory size. Then this determines the number of machines. In any case, the total memory space, the total space should be n log cubed n.
The
Right. This is a general assumption we use in this model. So the number of machines and local memory space, then the general assumption is that the total memory space is linear in N. And we usually use S as a parameter. Then once we have S, then M is determined immediately.
Can I ask a question? So, can you go to the slide with the sorting part? So, as of my understanding, in the MPC algorithm, we assume that each computer is distributed. So, the computing power and the memory are all distributed over the computers. But I guess you sample the items from the global memory. So, are we assuming that we can have an access to all the data, but we cannot compute it because it is too large?
No. We don't have a coordinator. I mean, those machines are independent. So each machine cannot access to the memory of the other machines. But we can sample those items in parallelly. For instance, for the first machine, we sample root S items. And second one, we also sample root S items. Then using these three, we can merge those samples in a bottom-up approach. If we merge the samples and then we sample again uniformly random, and we send it to the higher levels and so on.
So in that case, after the broadcasting algorithm terminates, every machine has a S number of the pivots.
Yes.
Thank you.
Do you have any questions? 네.
So I think intuitively, the number of bucket should be similar to the number of machines.
This is a single machine. Yes.
So one machine, one bucket.
Bucket? Yes. Yes, that's right. Yes.
Okay, and yeah, if you have more questions after the seminar, you can ask. Yeah, thanks again to the